Hello friends, in today's question. So today we are going to do 2016 advanced questions. Sorry, it is 2013 advanced questions, and we are going to solve two questions in it. So in the first question, we have a thermal power plant produces electric power of 600 kilowatt at 4000 volt, which is to be transported to a place 20 kilometer away from the power plant for consumer usage. It can be transported either directly with a cable of large current carrying capacity or by using a combination of step up and step down transformers at the two ends. The drawbacks of the direct transmission is the large energy dissipation. In the method of using transformers, the dissipation is much smaller. In this method, a step up transformer is used at the plant side so that the current is reduced to a smaller value at the consumer side, and a step up transformer is used to supply power to the consumer at the specific lower voltage. It is reasonably it is reasonable to assume that the power cable is purely resistive and the transformers are ideal with a power factor unity. All the current and voltages mentioned are the RMS values. So based on this discussion or rather passage, we have two questions. In the first part, we are asked that if the direct transmission method with a cable of resistance 0.4 ohm per kilometer is used, the power dissipation in percentage during the transmission is. And we have second part also. In the method of using the transformers, assuming that the ratio of number of turns in the primary to the secondary step-up transformer is 1:10, if the power to the consumer has to be supplied is 200 volt, the ratio of number of turns of primary to that of secondary in the step-down transformer will be. So we are going to solve the first part. And in the first part, we are given that the cable is having a resistance of 0.4 ohm per kilometer, and the distance is total 20 kilometer. Therefore, we can find the total resistance of the cable and this will be equal to, let us call that R total, and that will be equal to resistance of the cable multiplied by the distance. And resistance of the cable is given as 0.4 ohm per kilometer and multiplied by the distance, that is 20 kilometer. So we get the total resistance is equal to 8 ohm. Now we are given the power, which is it is given as 600 kilowatt. From here we can find out the current in the transmission line. Transmission lines is nothing but the cable. So you can say current in the transmission line, if suppose that is given as I, then I is equal to P divided by V. It is our 600 kilowatt, so we can write this as 600,000, and divided by the voltage is given as 4000. So the current will be coming as 150 amperes. Now we can find out the power dissipation in the cable, because we know the value of resistance and we know the current that is flowing in the cable. You can say power dissipation in the transmission line, or we can also call it as a cable. So let us write it as PD, power dissipated, is equal to I square multiplied by the total resistance. Current we just found out is our 150 amperes multiplied by total resistance, that is our 8 ohm, and this comes as our 180 kilowatt. So this is the power dissipation in the transmission line or cable, and we are asked to find out the percentage power dissipation. So from here we can easily calculate percentage power dissipation so we can write this as power dissipation in percentage will be equal to power dissipated divided by total power and multiply by 100, and we have this as 180 kilowatt, and this is our 600 kilowatt, and multiply by 100, and power dissipation in percentage will be coming equal to as 30%. So the option B is the correct option for the first part. Option B is correct. For the second part, and it is said that we have to find out the ratio of the number of turns in the primary to secondary in the step down transformer. So let us first of all deal with the step up transformer, because it is given as a ratio 1:10. So we start from there only. So step up transformer. So in this case, the step up transformer is going to increase the voltage from 4000 volt to certain higher value. And the ratio is given as, I think it turns ratio is given, let me check. Yeah, turns ratio. So turns ratio is given as 1:10. Therefore, we can find out the output voltage, which we can also call as a secondary voltage after step up transformer. Let us call that as V2. V2 will be equal to V1 multiplied by N2 divided by N1, and V1 is our 4000, and this comes as 10. Ratio is given as 1:10, so N2 upon N1. So this basically is our N1 is to N2. So we get this as 40,000 volts. So the power transmitted in the over distance of 20 kilometer, therefore we can find out the current in the transmission line. So you can say current in the transmission line If that is given as I, then that will be I divided by V2, and this is our 600,000 divided by 40,000, so it comes as 15 amperes. Now we are interested in stepped up transformer. So the step down transformer, and the stepped up transformer, it requires a 200 volt. So it means the stepped up transformer is going to convert the 40,000 volt to a 200 volt, and we can write once again using the transformer ratio, N3 upon N4 will be equal to V2 and divided by the supply which is required by the consumer. And V2 is our 40,000 and consumer requires 200 volt. So we get this as 200. Therefore, turns ratio will be equal to 200 is to 1. Okay. So this N3 upon N1 is written only to differentiate it from N1 by N2, that's all. Otherwise, sometimes it is also written as N1 by N2, N2 by N1. So the turn ratio comes as 200 is to 1. So option number A is the correct option. Option A is correct. Let us do the next question. It was also asked in 2013 advance. So here a point charge Q is moving in a circular orbit of radius r in the xy plane with an angular velocity omega. This can be considered as a equivalent to a loop carrying a steady current of Q omega upon 2 pi. A uniform magnetic field along the positive z axis is now switched on, which increases at a constant rate from 0 to b in 1 second. Assume that the radius of orbit remains constant. The application of the magnetic field induces an EMF in the orbit. The induced EMF is defined as the work done by an induced electric field in moving a unit positive charge around a closed loop. It is known that for an orbiting charge, the magnetic dipole moment is proportional to the angular momentum with a proportionality constant as gamma. So based on this discussion, we have two questions. In the first part, it is asked that the magnitude of the induced electric field in the orbit at any instant of the time interval of the magnetic field is. In the second part, the change of the magnetic dipole moment associated with the orbit at the end of the time interval of the magnetic field change is given by one of the correct option. Okay. So let us solve this question one by one. And we start with the Faraday's law of induction, and it tells us that the induced EMF in a closed loop is nothing but the rate of change of flux. So we say from Faraday's law of induction, induced EMF is equal to minus d phi B by dt. And the magnetic flux is our phi B. We can say that our magnetic flux, which is phi B, will be equal to magnetic field multiplied by area, and radius is given as A, so therefore we can write this as pi B pi r square. And it is given that the magnetic field increases from 0 to B in 1 second. Therefore, we can write rate of change of magnetic field. So we begin that magnetic field increases from 0 to B in 1 second. Therefore, we can write that dB by dt will be equal to B upon 1, which come equal to as B. So therefore, rate of change of flux rate of change of flux, we can write it as d phi by dt will be equal to pi r rather, and derivative of dB by dt we just found out is equal to B. So let me write it here, dB by dt, and this comes as pi square multiplied by B. Thus, we can write that the induced EMF is equal to minus pi r square upon B. So we are more interested in the magnitude, so we will just remove the, you can say this, we will not consider this negative sign. Okay, we are interested in magnitude only, and we can use the relationship between induced EMF and electric field. So we can say the induced EMF around a circular loop is related to induced electric field as, so we can write induced EMF is equal to, for a closed loop, E multiplied by E dot dl, and for a circular path of radius r, the electric field is uniform along the loop. So we can just extend it that electric field is uniform. So this comes as integration of dl, and the radius of the loop is given as r. So the small elements will be added, and that will be result in the circumference of the loop. So we can write this as E into 2 pi r. And induced EMF, we just found out the relationship, and we are only going to write its magnitude. So we can write this as let me call this as equation 1. So we can say, using equation 1 only magnitude. Therefore, we can write that electric field multiplied by 2 pi r will be equal to pi r square multiplied by b. And here pi and this r gives the square, so we get that our electric field is equal to r multiplied by b divided by 2. So I think this was asked in the first question. Yeah. So option number B is the correct option. Option B is correct. Now we come to the second part. And the second part, it is said that the change in the magnetic dipole moment associated with the orbit at the end of the time interval of the magnetic field changes. Okay, and the time interval magnetic field means basically it is of 1 second. So we start, and it is also given that the point charge q moves in a circular orbit of radius r in the xy plane. Angular velocity is given, and the most important part is that is given that the current equivalent is represented as q omega divided by 2 pi. This is the current equivalent. Okay, so we can say that I is equal to q omega upon 2 pi. So it is given that point charge q moves in a circular orbit, moves in a circular orbit of radius r. We are also given the angular velocity, that is omega. Is equal to omega, and the important part is the equivalent steady current. Equivalent steady current if we represent it as I, then I is equal to q omega upon 2 pi. And another thing that is given, that the magnetic field induced, magnetic field is along the z-axis. We can say that our magnetic field is, which is represented as B, is along z-axis. Is along z-axis, and it increases from 0 to B in 1 second. Increases from 0 to B in 1 second. And the important thing also given, that the radius is constant. R is constant. It is not going to change. Therefore, we can write that the magnetic moment it is given as constant of proportionality. Yeah, it is given in the question that the orbiting charge, the magnetic dipole moment, is proportional to angular momentum with a proportionality constant as gamma. So from here we can write a relationship that the proportionality between magnetic dipole moment dipole moment and angular momentum and angular momentum. So based on this, we get the relationship that the magnetic dipole moment, usually represented as mu, will be equal to gamma, that is a proportionality, and the angular momentum, which is represented as L. And we also know that the magnetic dipole moment is given as product of current as well as area. Magnetic dipole moment, that is our mu, is equal to current multiplied by the area, and the radius is constant, so we can write that our area will be equal to pi r square. And from here, and the value of current is also given to us. Based on this, we can find out the initial dipole moment. Initial dipole moment, let us call that as mu I, will be equal to, value of the current is given as q omega upon 2 pi multiplied by pi r square. And here pi goes with pi, therefore we get initial dipole moment is equal to q omega r square divided by 2. Now we can find out the induced electric field and the torque. Induced electric field and torque. So induced EMF, we already know the relationship. Induced EMF is equal to minus d phi by b upon dt. And flux, we also used this relationship previously. Flux is equal to b multiplied by a, and this gives us b pi r square because the radius remains the same. And the magnetic field changes. Once again, we can write that the dB by dt is equal to b upon 1, and this comes as b. Therefore, based on this, from here we can write that d phi b upon dt will be equal to pi r square multiplied by b. Thus, the induced EMF will be equal to minus pi r square multiplied by b. We did this entire calculation previously also. And this induced EMF is going to generate a electric field. This induced EMF generates a induced electric field. Generates an induced electric field, which is represented as E and along the circular orbit. Therefore, we can write the relationship that our electric field will be equal to induced EMF divided by 2 pi r, and we substitute value of induced EMF, which is our negative of pi r square b divided by 2 pi r, and this comes minus rb upon 2. and there will be as the charge, this electric field rather, will be exerting a force on the charge. You can say that induced electric field exerts a force on the charge. And let us suppose that force is given as F, which will be equal to charge multiplied by electric field, and we substitute the value of the electric field. This comes as minus of Q RP divided by 2. And this provides a torque. This force rather provides a torque. You can say this force provides a torque. And if that torque is given as tau, then tau will be equal to, and that torque will be about the center of the orbit. So we have this is R multiplied by F, and F we already know, so this comes as R minus QRP divided by 2. So we can write that our torque is equal to minus Q R square B upon 2. Now we can find out, because this torque is going to change the angular momentum, and we can say the change in angular momentum will be equal to torque and the time, that is about 1 second. So we can say that since torque changes the angular momentum, therefore the change in angular momentum over 1 second, because magnetic field only changes in 1 second. So you can say over 1 second, and we can write this as change, that is delta L will be equal to tau multiplied by 1, and this comes as minus Q R square B upon 2. And now we are going to find out the change in magnetic moment. So we have change in magnetic dipole moment and the proportionality relationship that is given as mu is equal to gamma multiplied by L, that is angular momentum. From here we can write that a change in magnetic dipole moment will be equal to change in the momentum. And we just find out the change in angular momentum, that is delta L. Therefore we can write that our change in the magnetic dipole moment will be equal to, we substitute value of change in angular momentum, and this comes as gamma minus Q R square B upon 2. So we can just combine it, and this becomes a minus, this is Q R square B gamma divided by 2. So this is the change in the angular momentum, change in magnetic dipole moment as the magnetic field changes from 0 to B in 1 second. and based on this you can see that option number B is the correct one. So we have option B is correct. Is correct. So these were the two questions based on 2013 advanced previously asked question of the JEE advance. So this completes these two questions. Thank you.